All right. So I'm going to talk about complex numbers probably for the last time formally as a topic, although we are going to talk about complex numbers for the rest of the semester, right? So the other day we started out with this problem here, right? So if I have sine x times cosine 4x, I can convert that into something that is related to exponentials. Now, again, that doesn't seem immediately obvious that that's a useful thing to do, right? But it does make a lot of math that we do ultimately easier. So we're gonna start talking about that a little bit more today. But if I look at this, what I did the other day is I used these two relationships, right? And there's a summary page, the Euler's identity summary or something like that that I posted that has those formulas, right? So what I did was at the very end, I basically said, okay, sine 3x, I can use this relationship for sine 3x. I can use this relationship for cosine 4x. And essentially what I did was I multiplied those two things out, okay? I multiply those two things out and I got this thing here at the end, right? So this kind of messy thing. All right, so what I want to do, I'm going to get rid of that right there. So if I look at what I've got right here, so I simplified this down the other day. So I had 1 over 4j e to the j 7x, and then I had minus 1 over 4j e to the minus j 7x. If I look at that, this result on the top here, right? I can group the terms like I did on the bottom. All right, now this is where I very quickly ended it the other day. If I look at this expression here at the bottom, I can relate those to a sine or a cosine, can't I? How can I relate those to a sine or a cosine? What should I do to try to do that? Let's just focus on the one. So I got the two square brackets there. How can I relate that to a sine or a cosine? It looks like, yeah, so it looks really similar to the equation I have on the first page, right? So in fact, which one of the two does it look similar to? This one or this one? The sine one, right? So if I look at this, it looks like I have 1/2 times 1 over 2j. So in fact, I'm just gonna write it this way. I'm gonna put a 2 here, 2 here, and a 1/2 there, right? Now, if I write it that way, right, I can see that what I have is 1/2 times sine of 7x. What about this one next to it there? What about that one next to it? Yeah, so it's x. So how would I write that? So it's a sine of x. What coefficient's on it? -1/2. Yeah. Now the context that I give you these problems, like in homework, the current homework 4, is I say, well, what if I do the integral of sine times cosine? I don't remember this off the top of my head. It's integral of sine times cosine like this. I think you would have to do integration by parts to do that, right? And it would be messy to do it. The integration of this, which it's equivalent to, is a lot easier, right? So that integration becomes a lot easier. Now, that's the fact that we're making integration easier is not really my main interest, because at the end of the day, solving integrals is not what most of you are ever going to do for a living anyway, right? But the notion of what we can do with complex numbers and this relationship between sine and cosine and complex numbers is useful. So that I want to talk about a little bit more today. All right. So with that, I'm done everything that's going to be on exam 1. All right. You guys have the material at this point. I'm going to jump over to my next topic, all right, for today, which is all about differential equations. That's not on the exam. All right. So everything I cover after right now is not on the exam. So let's jump into this. All right. All right, so take a second here to. Okay. All right, so you guys have seen differential equations. I say introduction to differential equations. You've seen them before, obviously. Hopefully you have. Whoa, trippy. Okay. Hopefully that won't keep happening. All right. You guys have seen differential equations before. Most likely when you solved them in the differential equations course that you took, you focused on using probably Laplace transforms a lot, which is not wrong. It's fine. But usually in engineering, we take another approach. We want to think about how to solve those using the idea. Some of you guys may remember this. What's the other approach you can do? So you do the whole thing with Laplace, but what else? What's the other methodology? You guys remember?
Characteristic equations to get your roots and then general solutions.
Yeah, characteristic equations, and then you get your general and particular solution, all that stuff. All right, we're going to review that a little bit, but I want to review it from kind of an engineering perspective a little bit. All right, so one of the things that we're going to get into as I look at this is all three of those circuits right there are equivalent circuits. Okay, so the one that you have right here, this one in the upper left, that's a circuit you could easily build in the lab, right? You could go upstairs right now and you could get a resistor and a capacitor and you could put them on a breadboard. And A cosine omega t plus phi, where would that come from? If you had to go into the lab, where would you get A cosine omega t plus phi? Function generator, right? If I get a function generator up in the lab, right, that's basically A cosine omega t plus phi that I can plug in there, right? And that circuit is a real thing I could build. There's a voltage source that could have a voltage that had that shape. Now, what I can't build is what I have shown right here, right? I can't build an e to the j omega t voltage source. Why not? Because it's imaginary, right? However, I can say that these two things are equivalent. Why? Why is that circuit on the top left and the one on the top right? Why are they equivalent? Yeah, if I look at superposition, right, the principle of superposition, if I take this bottom source here the top source and the bottom source and put them together, I have A over 2 e to the j phi e to the j omega t plus A over 2 e to the minus j phi e to the minus j omega t. That is the voltage across those two things. If I went in, that's the voltage right there. If I put a multimeter across it, that's equal to A cosine omega t plus phi. Okay. In other words, I can make a voltage that varies sinusoidally. It goes up and down and up and down. I can't make e to the j omega t, but it's okay for me to think about that A cosine omega t plus phi as the sum of those two rotating vectors. And the sum of those two rotating vectors is a pretty useful thing for me in terms of how it simplifies the math that I do from this point forward. Okay, we're going to get into that a little bit today. Now, the other thing is this same thing is equivalent to the real part of A e to the j phi e to the j omega t. Where what's the thing we called the static phasor? What was that piece? Yeah, A e to the j phi, right? And again, in 2112, you're going to use that thing and call it the phasor. And in fact, for the most part, you won't even use the e to the j part. You'll just say it's a magnitude and an angle, and you'll put it in polar form for the most part. Okay. All right. So we're gonna try to use that as we go through and look at the differential equation stuff. All right. And we're gonna see why today at the end. All right. So in terms of what we're gonna cover, I want to cover some basics. Like differential equations are pretty important, and why. And we talk about that a little bit. We'll do that today, and I'm going to start talking about first order stuff. All right, in the book, this is section 7.3, and then we're going to talk a little bit about second order equations, which is 7.4. And then there's this general properties I talk about. That's not all that important. I'm going to focus primarily on these two and this guy, numerical solutions. So we're going to look at using MATLAB and numerical techniques to solve these. And a big thing that you're going to be doing in the project is this. All right, is you'll be doing some numeric solutions. So we're going to talk about how to use a tool like MATLAB to be able to do this. Now, one thing that always kind of comes up, I am never asking you to solve a differential equation in MATLAB. MATLAB has some way of doing that. I don't know what it is. Like there's a symbolic toolkit of some kind that'll do that. There's a symbolic toolkit that can integrate and differentiate and all that kind of stuff. I've never once asked you to do that. So don't start trying to use those unless you want to. But I've never in a homework assignment asking you to use one of those sorts of things. You should be able to basically go through and solve the differential equations by hand, and then you make the plots to submit your homework and stuff like that in MATLAB. All right. So we'll talk a lot about the numeric stuff because that's a big part of the project. All right. So I want to compare the two types of systems we have. There's the boring, stupid systems. That's what you learned in 2111. All right, the boring, stupid ones, which is this guy right here. Basically a 9-volt battery and a couple of resistors. Now, I said this is a boring, stupid system. What if I turned the 9 volts on? So if I call this here V of T, that's my power source. So I hook a 9-volt battery up there, and let's say, here's the way I'll think about this. At time t equal to 0, I connect the red wire on the battery to my resistors. So that means that the voltage V of T would go from 0 to 9 volts suddenly at time t equal to 0. All right, that's what the voltage looks like there if I turn the voltage source on. Which with a 9-volt battery, turning the voltage source on, if I want to model that, you're basically mathematically modeling sticking the red wire into the breadboard. Okay. So what's I of T, the current in this circuit, look like? What would that look like? You don't need to worry about giving me a number. I don't care about the number, right? The number is tricky to calculate. It would be 9 divided by what? 18K. All right, what would it look like though? Not quite a constant, you're almost right. Well, it wouldn't slope upward, right? It would be flat, right? It would be a constant, but it would be a constant starting at time t equal to 0. When I turn the power on, that's when this guy starts going. Okay, the current's a flat thing. So in this case, I got 9 volts and 18K. So I think that's, well, I'll just call it 9 volts divided by 18K. What is that? Is that 2 milliamps or 0.2 milliamps? All right. One or the other, but so 0.2 milliamps, even that's a big current, but by electronic standards, that's a big current. By Duke Energy, that's not a big current. All right, but for an electronic circuit, that's actually pretty big. Okay. I call that a static system. Why? What's that? Voltage doesn't move, the current doesn't move. Basically, if I apply a DC voltage, I get a DC current right away, right? It happens instantaneously. The current and the voltage instantly track each other. If I take that 9-volt supply and I take it to 10 volts, the current just goes straight up with it. There's no lag to it. In other words, what does this system not have? In terms of, let's put it this way. This guy is what's he doing with energy? Energy leaves the 9-volt supply. And what happens to the energy that leaves that 9-volt supply? Where does it go? In this system. So you don't like the word energy, but power is the same thing as energy, right? There's power that leaves that 9-volt supply. Where's it go? Dissipated as heat in those resistors instantly. They just start to heat up right away. The other type of system I have is a dynamic system. And what's a dynamic system have? Energy storage. All right. Energy storage makes the world complicated and interesting, right? If I just had resistors, I'd have a lot of light bulbs and a lot of heaters, and that'd be about it. right? I wouldn't have much useful stuff, but energy storage is what makes everything get more interesting. All right. And so energy storage is dynamic. All right. So I want to think a little bit about why we cover them so much. So where's the differential equation actually kind of come from? All right. If I looked at a car, all right, this is my really bad car. All right. So it's a box on wheels. And let's say my box on wheels, this guy stores energy too, doesn't he? What's the energy? So if my car is moving at a certain velocity, V, right? What's the energy stored in that car? Kinetic energy. Yeah. And what's its form? 1/2 mv squared. All right. That's the energy stored in the mass of that car. So what that says is it's a heck of a lot better to get into an accident at 5 miles an hour than it is at 10, right? The faster and faster you go, the more and more screwed you are, because the velocity squared, the energy goes up a lot faster, right? There's something crazy about any kind of energy storage thing that you look at. 1/2 mv squared is the energy stored in this thing. What about the capacitor over there? What's the energy stored in that capacitor? 1/2 C V squared. I'm going to call it V sub C to sort of differentiate. Something kind of magical about the way the universe is structured, right? Is that any kind of energy storage device I have, the energy stored in it is always 1/2 times the energy storage element times whatever it stores squared, right? The thing that gets stored in a capacitor is voltage, right? The thing that gets stored in a car, in a mass, is velocity, right? So it always has this kind of general form. And whenever I have energy storage, some weird stuff kind of takes place, all right? So let's just think, if I had a car going down the side of the road like this, my crappy box car here, if I suddenly stopped pushing the gas on that car, what happens to the speed? Slows down. It doesn't do it right away. No, it doesn't slow down right away, right? What if I just was on a flat surface like this and I let go of the gas, eventually I'd stop, right? But it would take a while to stop. What's causing it to stop in that case? Friction, right? And it's the friction probably of my really ugly boxy car. There's probably a heck of a lot of air friction hitting it, right? So it's going to slow down pretty fast. There's also some friction on the wheels and stuff like that that's causing it to slow down. So I could write a differential equation for this thing, right? The way that I would think about this is it takes it a while to slow down, all right? And what's happening is the rate at which it slows down changes over time, right? So the origin of differential equations basically kind of give rise, or they come from the fact that I have these energy storage things. And if I have something like a capacitor or a car like this, if I took a capacitor, let's say, and I suddenly, all of a sudden, tried to make the voltage on a capacitor go to 0, okay? I don't know if they still ever do this for you at any point. Do you ever seen this demonstration? If I take a capacitor and I try to make it instantaneously discharge, right? Let's say I put a screwdriver across the terminals. What happens? Sparks, right? The most common thing probably is if you had something like a hair dryer plugged in. A hair dryer is pretty beefy load. If I had a hair dryer plugged in, I pulled it out of the wall, right, while it's still turned on, what happens with that? It doesn't have to be a hair dryer, but a hair dryer's got a lot of juice to it. It could be a toaster, it could be anything. If I quickly pull that out of the wall, what do you see? A spark. Why do you see a spark? Well, it's got what discharges. If I pull, what is a hair dryer? I mean, what's in there? A motor's in there. What's drawing all the current in a hair dryer? Not the motor. The motor's actually, there's a little fan blowing air, right? There's a resistor in there, and that resistor, the heating coil, is pulling a lot of current, Where's the energy stored there? There is energy storage in that thing. Where is it? There's a magnetic field around that wire. So there's some inductance in it, right? If I suddenly pull a cable out of the wall and there's energy stored in an inductor, what's the thing about energy? Energy doesn't like to just be destroyed, right? It has to always, energy is always conserved, right? So it has to go somewhere. So if I suddenly make energy go away, right, what's going to happen is it's going to change its form to some other form. So if I had charges that were creating energy, right, so I had magnetic fields where I was storing energy, and I pull that cable out of the wall, what's going to happen is I'm going to make light, right? Because energy is going to immediately say, I had this energy. God said that's the way the universe works, right? I have no choice but to change myself from one form to another. All right, that's the way it goes. So if I have this basic relationship here in any of these things, one thing that's always true in any of these things is the voltages and the speed here always have to be continuous. I can never have big jumps. If there's a sudden jump in a voltage on a capacitor or a sudden jump in the speed on this thing, there has to be a change, okay? And that change basically, like if I stuck a screwdriver across here, I would have to get a sudden flash of light or something like that, where the energy that was stored in the field basically becomes now light, all right? So that principle is really important, right? And it's what defines everything that we do about solving differential equations. What does it mean? Where does it, what the thing that always kind of comes in here, and the thing is probably really important, is if I look at this, let's say I wanted to figure out what the current's going to look like here in this circuit, okay? What would the current look like in this circuit? So here's I of t. And I guess I want to figure out really what's the voltage on the capacitor. Let's say the capacitor is charged up to some initial value, 10 volts. How would I solve for what the voltage is going to look like in that circuit? How would I figure that out? What's that? KVL, right? I'd say, 0 equals the way that is, I don't know, normal. I don't know what they're doing all the time these days, but I look at this and I say, well, V sub C, so I go minus V sub C plus whatever I have going through this resistor. So for this resistor, I have I times R. So I'll call that R, like that. What's I in this circuit? What's that? Yeah, it's current, but what's the formula for it? C dV dt, all right? And because that current flows out of the plus sign on the capacitor, right? This would be minus V sub C minus RC dVc dt. All right. And I put a negative current in there because it's the current's coming out of the plus sign, right? So that means that in this circuit, V sub C is negative RC dVc dt. Okay. In words, what does that mean? What does that tell me about the voltage on the capacitor in this setup? What's it mean about that? Well, yeah, the voltage, the energy storage stuff is what makes it have to be continuous, right? And then that's a really important point. But this particular expression has a physical meaning. And to you guys, at the end of the day, you're never going to remember to solve differential equations. I know a lot of people who are good engineers, right? And I put this on YouTube, so I should be careful. My wife's an engineer. She can't solve a differential equation to save her life at this point, and she would admit that, right? Doesn't make her a bad engineer, right? What you do and hopefully that part will get posted. But the part that's important is what the heck does that thing mean? You guys don't like to focus on that because you're worried about what grade you're going to get, right? But what does this mean? Physically, that part actually is important. What does that mean? Tells me the voltage on the capacitor is related to what? They're related to what? The derivative?
The time constant.
Well, it's related to the time constant. What else? Yeah, so basically the voltage on the capacitor is proportional to how fast it's changing. All right, so how fast the voltage is changing tells me what the voltage is going to be at any point in time. This energy storage element is what does this. What it means is the capacitor has memory, right? It remembers what happened in the past. So that what I have right now on a capacitor, what I have, the voltage I have on it depends on how fast it was changing right before that. So if I looked at the voltage here, you should know this, right? If I started at 10 volts, where does it end? 0. And what's it look like on its pathway there? What's it look like on its pathway there? Exponential decay, right? And where does it, where is its fall fastest? Is it falling faster at when it's up near 10 volts? Or is it falling faster as it gets towards the end? 10 volts, right? Why is that? It's gonna look like this, it's gonna level off. Why is it falling faster right here? Because the rate of change, right? The rate of change is directly proportional to how much actual voltage I have on that thing. All right. And so anytime I have an energy storage element in any real system, a dynamic system, right? Basically what I end up having because of this energy storage, and this is the important thing, because of this energy storage, like if I think of a car accelerating down the road and I let off the gas, this guy is going to take some time to slow down. Because of the energy storage that's in this system, anytime I try to use the system, there's going to have to be essentially a response that comes from this, the fact that it takes a finite amount of time for the energy to change from an initial state to a final state, right? On a capacitor, on that car, I can't instantaneously change the speed of the car from 0 to 60. It just can't happen, right? Get into a Tesla, it'll happen pretty fast, but it's not going to happen instantaneously. It always takes a finite amount of time because you can't change energy in 0 time. So this is where this manifests itself in any system. The fact that the thing that's stored, so the voltage that's stored on a capacitor doesn't just, like in this case, the voltage is equal to I times R. If I turn the voltage on, the current appears. In this particular case, if I had a circuit like this one, and I applied 9 volts to this RC circuit, that capacitor is going to get to 9 volts, but it can't do it right away, right? What's the capacitor effectively doing? It's charging up, it's fighting back, basically. It's because of the energy storage, it basically tries to keep its energy constant. Not constant, but continuous. So it fights back initially. A field is created inside of that capacitor to try to oppose the change. And because of that opposition to change, it takes a finite amount of time for the energy to change. And so there's always, anytime I have any real system, there's always some response that reflects this finite amount of time it takes to change. What do I call this? In math class, you had sort of a name for it.
It's the transient response.
Yeah, it's the transient or or in differential equations, I would call this the homogeneous. And I think your book calls this the characteristic. All right, but that all kind of mean the same thing. Characteristic, because what that response looks like is defined by the parameters in the circuit. It's characteristic of the circuit. Okay. All right. And there's always going to be a response that comes directly from the input. And that one's usually the easier one to figure out. Okay. All right. So this stuff matters in any real system, even in computer engineering. So I like to focus back onto some things related to computer engineering as well, right? When I look at this here, those are inverters, right? So if I think about computer hardware, right? I think of zeros and ones, but those zeros and ones are real voltages that exist somewhere, right? So I have 5 volts, 0 volts, right? So 5 volts might be a 1 and a 0 volt might be a 0. So if I had that right there as my VI, right? This guy in computer hardware, this would be some kind of transistor or something like that, or a combination of transistors. What would VO look like here in this circuit? What should it look like? Right, so it's an inverter. If I give an inverter a 0, what do I get out of it? A 1. If I put a 1 into it, I get a 0 out, right? So if I look at this in time, right? If I look at this in time, I would see 1, 0, 1, like that, right? So I'd see, but this would be a voltage, okay? So VO would look like this, and time would look like that. That looks like kind of a staticky sort of system, right? Because what I put an input in and I get something out. Now, is it really a static system? Do you think? In other words, so a static system I said was one that basically responds to me instantaneously. I put an input in and the output, in this case, the output's the current, output changes immediately. All right. Is that what I have here? Do you think? You think VO, as soon as VI becomes a 1, does VO immediately become a 0? Should it? You guys actually, I don't even really do this anymore. Do you actually use NOT gates 7404s in lab ever? Yeah. Does the output immediately change? Should it? Any ideas? It's not that tricky of a question. Decent guess, right? So it won't change right away, but it might within, I don't know, 10 nanoseconds or a nanosecond, right? Think about it for a second. This is pretty typical of what I might have in a computer, right? Let's say I had a computer with a 1 gigahertz processor, right? What's the period if I had a 1? So 1 gigahertz, basically, there's a square wave inside that thing, and it's a periodic waveform, right? So if it's periodic and it's got a frequency of 1 gigahertz, what's its period? What's its period if it's 1 gigahertz? So 1 gigahertz is 1 times 10 to the what? If I had a gigahertz. You should know this. What's a you don't see giga much in physics, I guess. 1 times 10 to the 9th. Yeah, it's 10 to the 9th power. So if I'm 10 to the 9th power, what's my, so F equals 10 to the 9th, right? F equals 10 to the 9th hertz. What is the period? 1 nanosecond. All right. If this is a wave that's changing every nanosecond, all right, it better change pretty much instantaneously, right? I mean, you would probably consider a nanosecond to be instantaneous, right? But that's not quite what's going to happen. Okay. If I look in this is what I would ideally have. Here's V sub I, here's V sub O, right? Ideally, if V sub I was 0, 1, 0, 1, I would get 1, 0, 1, 0, 1 like that. Now, this is what I get in the real world, right? What I get in the real world is when V sub I changes, I see V sub O has a response like this, kind of rounded off like that. What's that look like? This is exaggerated. It wouldn't quite be like this, right? But what's happening here? Why doesn't that look like a pure square wave? What's got to be happening there? Well, it takes a little bit of time to change, but why would it take a little bit of time to change?
Because they're not ideal conductors.
Well, yeah. So what I tried to draw in here is there's effectively going to be there's charges that are moving here, right? And so particularly if I look really carefully at what's inside of an inverter, what I would actually see is it's got this funky little device called a transistor, which electrically is a switch, but at this point right here, there's a little bit of capacitor there. Okay, so there's some electric field that needs to be stored. I also showed here I got currents moving through the wire, right? If I have currents moving through a wire, I have a magnetic field around those wires, right? Any wire in the world has what? Inductance, right? Every wire in the world has an inductance. And so there's actually, if I look at this, there's actually a second order system, right? There's actually there's some L and some capacitance, which actually means that it's possible that V sub O might look like that. All right. So hopefully you guys have seen this before. We're gonna cover this. This is, let's see if you have seen this, what kind of response for a second order system is if I have something like this, which is jumpy like that. What's that called?
An underdamped response.
Yeah, this is an underdamped response. Okay. Where basically this guy overshoots and undershoots like that. That can only happen if I have a second order system. Okay. Second order system means what? What does it mean to have a second order system? So two derivatives, which is a correct answer. Very math answer though. Physically, what's it mean to have a second order, two derivatives? How do I get a second order system? Yeah. Yeah, I got to have two different energy storage elements. So in a real, say, chip, right, I have some inductance and capacitance I have to worry about. So this is a problem actually you're going to look at from a design perspective, and you're going to deal with it numerically in the project, right? Something like this. Okay, how do I think about trying to mitigate those problems when I'm trying to design? All right, and so you're gonna do a little bit of playing around with that in the project. All right, so if I looked at a real setup, right? Effectively, what I'm saying is I could model this guy as having some capacitance and some inductance, and say that the total system actually looks something more like that. All right, so we'll talk about that with the project. What I want to deal with is ultimately, let's say I have this system right here, all right, and what I want to do. Skip ahead. All right. Yeah. Okay. All right. I want to deal with looking at this particular circuit, and I want to figure out how do we solve the differential equation that's going to come out from this. Okay. So RC circuit, voltage source input like this. How do I figure out what's the thing you typically end up solving for in a circuit like this? It's the capacitor voltage, right? So in this case, how do I write the differential equation? What's the process to start for solving this thing? KVL again, all right? If I'm ever writing KVL, when I do circuits, before I do anything, I say which directions do I think my voltages are. I write my pluses and minuses like that. And the current in this circuit, I'm going to say is going that way, I sub C. So I know that I sub C equals C dVc dt. All right. I'm going to say 0 equals what? Now, the way I do this is I start in this corner and I go around clockwise. So I say 0 equals minus Vn plus the voltage on that resistor, which I'll say is I times R plus V sub C, like that. So I get Vn equals IC times R plus V sub C. And that's not a differential equation, is it? How do I make that a differential equation? What's missing? The derivative, right? So how do I get the derivative in there? Yep. So RC dVc dt plus VC. Okay. Now, in this case, let's say my Vn of t was, all right, so I want to think of it like this. I want to think of it as having a 9-volt battery and a switch that I close at t equal to 0. All right, so let's say this guy is 9 volts like that. Okay, and this is my V of t. So the way you typically think about this is I have 9 equals that, like that. Now you guys should know what's the solution to that going to look like? What would V sub C have? It'd have an exponential, right? What's the final value of it going to be? So it's got, would be what? 9, right? V sub C would be 9 volts plus some value like that, right? And in general, the way I think about this is there's always 2 pieces to these things. So that's what I said before, the total solution or the general solution I get anytime I have one of these things is basically going to have some value, which I call the steady state solution. Okay. And then this guy here that I call the transient solution. And this guy is proportional to what I call the vanishing difference between that initial and final value. In other words, what's true about the transient response always? If I wait long enough, what happens to the transient response? Better go away. It's transient, meaning it's vanishing. It should disappear if I wait long enough. In fact, what the whole principle of 2112, as you get into 2112, the whole principle of it is that the transient response doesn't really matter most of the time. All right. So in 2111, you learned how to deal with resistive circuits, and then you started learning about transients. Well, for the most part, we don't worry about the transients, and we worry only about the steady state stuff. And when I worry only about the steady state stuff, and my inputs are typically sine waves, that's when complex numbers get to be really useful for us. All right, and that's again where we're trying to get towards, trying to understand those complex numbers better. So anytime we have these things, there is a general approach that we'll take, and I know you guys learned a couple of different ways to skin this cat when you were in differential equations. It's basically a 3-step process that we're going to take with everything in here. You'll see this on homework 5 and homework 6, basically our 2 differential equations homeworks. You're going to follow this basic approach each time. I'm going to ask you to figure out what's the homogeneous solution or the transient solution. I solve for that. Okay. And then I try to figure out this. I try to solve to get the particular solution. Okay. And the way that we're going to get the particular solution is using something called undetermined coefficients, which is a fancy way of saying we're going to do what? When I try to use this undetermined coefficients, if you learn, you should have learned that term in differential equations. What's it mean I'm doing with my answers?
AX squared plus BX plus C.
It could be. It all depends. Basically, so it could be that basically I'm guessing. I guess that the answer is going to be something, and I got to make a good guess. And I don't know exactly what it is. There's some coefficient that's undetermined, and I got to solve for it. All right. Basically, this is where I guess a solution, right? And that guess is pretty easy to do, right? If I have a circuit that has a constant input, what's the steady state solution going to be? Is it going to vary as a function of time? Okay, in this circuit, if I have a constant voltage source, this is my input, the voltage source. What's the steady state voltage on the capacitor going to do? Can it vary as a function of time if I have a constant input voltage? No. So I guess that the voltage is going to be constant, right? Constant input, constant output. If I have a sine wave as the input to my circuit, right? If this guy was a sine wave like this, what's the voltage going to look like in steady state? It's going to be a sine, okay? If I put an exponential voltage source into my circuit, I'm going to get an exponential voltage source out, right? The circuit doesn't do any kind of magic to change the input, right? The output of any system like this with energy storage, if I put a constant in, I get a constant out, right? If I put a sine wave in, get a sine wave out, right? That's actually what makes that's what makes the complex number thing really work out well for us. Because if I have a sine wave going in, the only thing that's going to change about that sine wave is its magnitude and its angle. So the only thing that's going to change is its phasor. All right, that static phasor is the only thing that changes. And that's what makes this thing become useful to us. All right, so essentially, we always guess that our output is going to look like our input. Okay, so in other words, this particular solution, what I call this is the steady state solution, right? The steady state solution looks like the input. All right, and that's important. At the end, what I have to do is I have to put them together and then solve for whatever's unknown at that point using the initial condition. Okay. So one thing that always screws people up is I got to put them together before I use the initial conditions. All right. You can't just use one to solve for the initial conditions. Okay. All right. So in general, all right, what we have, just a couple of terms, right? We have, I call this in general a non-homogeneous differential equation with constant coefficients. What does it mean to say this guy? I guess I wrote it here. To say that it's non-homogeneous means what? There's
Not equal to zero.
Not equal to zero. There's some in engineering terms, what we say is that there's some input or driving function. There's something driving this system, right? That's the terminology we use. All right. An equation without a driving force basically is something like my car after I let off the brakes or after I let off the gas, right? That car is now a system without a driving force. The engine isn't moving it forward now, right? But it's still moving, right? This is now a differential equation that's homogeneous, that describes this thing. If I hit the gas again, it becomes a non-homogeneous equation that describes it, right? Basically, that's how it sort of, the math relates to the physics. Okay, so couple of key ideas that I always think about here, and I touched on this already, right? There always should be as many derivatives as you have energy storage elements, right? Okay, an RC circuit 1, LR circuit 1, LRC circuit better be 2. All right, and the number of energy storage elements directly relates to how many exponentials I have in my solution. All right, now, you know that I get a single e to the something t whenever I'm dealing with an RC or an LR. You've done a lot of those. You guys should be doing LRC stuff now, probably in 2112. Yeah. I say always 2 exponentials. All right, but you guys probably know 3 different forms for those solutions, probably from 2112. Right? What are the 3 different ways of looking at those in 2112? What are the 3 terms we use in 2112? Better remember? Probably what you're doing like right now, maybe. Maybe you did it in the past. Hopefully you did it in the past. Overdamped, underdamped, and what's the other one? Yeah, critically or stupidly damped, right? Critically damped never happens in the real world. So I sometimes say stupid, right? Because it never ever happens. But the other 2, overdamped and underdamped, happen a lot. Now, what's overdamped look like? What's the overdamped look like? And underdamped. Again, no one is ever going to expect you to remember the formulas for that, right? In your life, you're never going to need to know those, but you should know what's the difference in underdamped and overdamped system. You had to describe it in words. What's the difference? Underdamped, well, they all have complex numbers, but yeah, I see where you're going with that. Underdamped, basically, I'm going to get roots. My roots are going to be complex, right? And what's it going to look like?
Sine wave.
Well, actually looks like two exponentials, right? And you're right, it's going to have a sine, it's going to have a decaying sine wave, but this guy is going to have an e to the st. This guy is going to look like this. So you have this decaying sine wave of some sort, but there's going to be an e to the s1t and an e to the s2t in both cases. In the overdamped case, it might look like that. Still looks like an exponential. Underdamped, it's still exponentials. It's just those exponentials are complex exponentials. And those complex exponentials mean that I get sine waves. Okay. Something we've already kind of known, but we're going to look at from a more mathematical perspective because we need to understand that piece. There's still two exponentials no matter how I look at it. It's just that in the one case, those exponentials can be related to sine waves. All right. We're going to deal with three types of inputs. All right. Cosine inputs or sine inputs, right? And then exponentials, and then this other guy here I called u of t. All right, u of t has a special name in circuits and ECE sort of problems. U of t is what I call the unit step function. All right, what is the unit step? You guys heard that before? What's the unit step look like? It's 0 when time is negative. So I say u of t is equal to 0 for t less than or equal to 0, and then it's 1 for t greater than 0. All right. And it's a little weird to say which one, where do you put the greater than or equal? You kind of do it on the other side. At the t equal to 0 part, is a tricky thing. All right. But this guy would be this, would be like this. The number 1. Now, this is a mathematical way of saying basically if I had a voltage source and a switch, what I'm modeling is the switch closing at t equal to 0. So sometimes from a math perspective, it's easiest to say that this is equivalent to a voltage source u of t. Those are the same things. Right. So and that allows us to use a lot of math tricks if we can take this switch and get rid of it and replace it with this u of t voltage source. All right. Now notice all of these things here have u of t in them. Right. Why do I multiply it by u of t? What's it mean to multiply it by u of t? If I take a cosine and multiply it by this guy right here, what's that make that cosine look like? What's it do to it? What happens to cosine before t equal to 0 if I multiply it by this u of t? It's going to be 0 before t equal to 0, right? So it's not going to be there. So basically it's modeling a switch, right? It's modeling the fact that any voltage source I have has a switch to turn it on, right? All right, so what I want to do is I want to solve if I've got a cosine input here. And I want to say what happens in this particular circuit when I have that scenario, okay? All right, and we should know that there's going to be two pieces to this thing. So we wrote out before, all right, that this guy has the differential equation. If I called this, I put this in sort of more math form, right? My input is X, my output is Y. Y is the voltage on the capacitor. So we wrote this out before. Basically, we said the voltage on the capacitor, or my input voltage, was RC dV CDT plus V sub C. What I'm doing is I'm saying, all right, I'm going to write this as my input X is equal to some constant times the derivative of the output. plus y, right? So basically, x is my input. And we keep it general. In this class like this, we're learning about the tools. So I'm not going to think of them as voltages and currents. I'm going to say inputs, outputs, right? It's a very general way of thinking about stuff. It's a systems way of thinking about stuff, right? Which is a way of thinking that we use all the time. All right, so this guy has two types of solutions, right? He's got two pieces of solution, right? And I talk about my process here. So I solve for the homogeneous, solve the non-homogeneous, and then find the total solution. So the homogeneous is this one here, right? I don't like that term. I like to call it the transient. Reminds me that it goes away, right? That it ends and goes away at some point. And then there's the steady state piece. Okay. All right. So I want to solve for those two things. Now, if this is my input, a cosine omega t plus phi, what's my steady state output going to be? What's my steady state output end up being? Won't be zero. My transient will eventually become zero. What's my steady state going to look like? If I put so the important thing is that anytime I have an input going into a circuit that has energy storage, there's two parts. One's the transient. That ends up being exponential every time, right? The other is the steady state. The steady state comes from the input, right? So the output is always going to look like the what in steady state? The input. Output and the input are going to look like each other, which mathematically means if I'm putting in cosine omega t, what's my output going to look like? This could be a sine wave too, right? And I'm going to say that my output ends up looking like b cosine omega t plus phi. I'm going to guess that as my output. Okay. I'm going to guess that as my output. What does that mean? So I get a cosine at my output in steady state. And what's that cosine look like? How does it relate to my input? How fast does my output and my input vary? In other words, what's their frequency? A cosine omega t, b cosine omega t plus phi. What's their frequency? It's the same, right? There's no difference. If I put a 1 hertz input, I get a 1 hertz output. What about the amplitude of those two things? The amplitude and the phase of those two things. Well, this guy, what's the phase right here? What's the phase angle of this? 0. Phase angle of this guy, I'm saying, I don't know what it is, but it might be different, right? Because of the effect of this capacitor, it might be different. I also am saying that because of Ohm's law and all that magic, its amplitude might be different. All right, so its amplitude might change, so it might get bigger or smaller. And the fact that I have a phase shift means that it might do what? Move left or right, right? So it could move in the time domain, left or right, and it could get bigger or smaller. Right? That's basically what that's saying. All right, so what I want to do is I want to think about how to solve this guy. So this is my equation here. The first thing I want to do is get this transient or characteristic or unforced response. So if I have this, how do I figure out what y sub c is going to be? Now you already know what y sub c is going to be, right? But how do I actually figure out what y sub c is going to be? You know it's going to be an exponential. How am I supposed to really figure that out mathematically? I guess, don't I? What do I guess? What's a good guess for this thing? If I want to guess what y sub c is, give me a guess. Well, you know it's an exponential. So y sub c of t looks like what? Definitely not -1.
Would it be AE to the negative T over tau?
Well, if I really don't know, I'll say AE to the ST, right? And I'll say, as long as I choose A not equal to 0, like that. And yeah, and as long as I choose that, okay? Now, if I put that in there, right? So I get d by dt of a e to the st plus little a times a e to the st. And let me not use a, because I guess I've already, I don't know, I'll c e to the st. Like that, right? What's the derivative over here? This guy, what's this derivative? Yep, s c e to the st plus a times c e to the st. Now, when I look at that, I got a common factor there, a couple of common things, don't I? What's common? What can I factor out? Yeah, c e to the st. So this guy becomes s plus a times c times e to the st. So I got three things multiplying each other there, right? And what do I know about c? So if I have three things, a times b times c all equal to 0, one of them has to be 0. Only one of them has to be 0 to make that work, right? So is the number c, that constant, is that ever going to be 0? No, because I said I can't. That's a dumb choice, right? E to the st, is e to the st ever 0? Mathematically, no, it never is. A t equal to negative infinity, whenever that was, back before the Big Bang or whatever, right? That whenever that happened, but I can never get there, right? So e to the st is never 0. So the thing that has to be 0 here is s plus a has to be the one factor making that 0. So that means that s equals negative a, right? So what I end up with is that y sub c, very simply, is e to the negative a t, okay? All right, so that ends up being that piece. Now the particular response. And I don't want you to know this per se, all right? I put this here. I'm never going to ask you to do this approach, but this is the way it's supposed to be, right? I say, if I have this equation, my guess is this guy right here, b cosine omega t plus 5. All right, and what I have to do with that is I got to expand that guy out using trig functions. Okay, and I end up expanding this, and so what I do is I take b cosine omega t and I get ready to plug it in here, and I take this a cosine omega. So I take this thing here, and I plug it into the differential equation. And that's what happens when I plug it into the differential equation. I took the derivative of b cosine omega t plus phi, and I got negative omega times the sine. So then I get this utterly ugly equation here. All right. Then what I have to do is I got to use trig identities to take sine omega t plus phi and cosine omega t plus phi. I use some trig identities, right, that basically allow me to take sine omega t plus phi and cosine omega t plus phi to break them down into these things. That takes this relatively ugly equation and makes it, I would say, uglier, right? So basically what I end up with is I use these expressions from trig identities, plugged them into here, right? And then got this whole thing. All right, now, what I do with that is I combine like terms. In other words, I look at this guy and say, well, there's a sine omega t term and another sine omega t term. And then there's a cosine omega t term and another cosine omega t term. And then over here on this side, I got a cosine omega t term. And I have 0 sine omega t terms. Okay. And then what I do is I group all the terms on here and figure out that the coefficient a has to be equal to this. And the coefficient 0 has to be equal to this. I put that together. I end up drawing a triangle and all sorts of stuff to figure out what is phi from that triangle, what is B from that triangle? And by the time I get through this whole thing, which I don't really want to spend time going through, but the whole thing I end up with is that I get that B equals A over omega squared plus A squared. And I guess it probably has, yeah, it ends up with this, right? Bottom line is, and then I also get that phi somehow is, I didn't put it, yeah, phi ends up being minus arctan of omega over A. A lot of work, all right, and I skipped over it, right? Because I did it very quickly. I would draw a triangle here. I'm not going to ask you to do this at any point. I think hopefully the only reason I do this is the one thing I think we can all agree on is that this would be very annoying to do on a regular basis, right? Everything I did here, we did trig identities and derivatives, all the fun stuff that you guys don't like to do on a regular basis. No one likes to do this on a regular basis. So this process gets old for us, right? But at the end of the day, what I end up with is the fact that this is the important thing, put a cosine in. What did I get out? I got a cosine out, right? I put A cosine omega t in. I got B cosine omega t plus phi out. All the work that I did was to figure out B and to figure out phi, right? There was a lot of work there, but if I now change my attention and say, you know what? And this is what it ultimately ends up being, right? But if I take this approach and I say, you know what? I'm actually going to view this guy being the same thing, right? I take that A cosine omega t and I replace it with these two vectors. This becomes a heck of a lot easier to analyze, right? How so? Well, if I told you I had A over 2 e to the j omega t equal to A times dy by dt plus y, where this voltage on that capacitor is my y, right? What would you guess as the steady state solution for this? What would you guess as the steady state solution here? What would be my steady state guess? All right, so constant is my input. What's my output look like? So 9 volts in, I get 9 volts out, right? Constant in, constant out. Cosine in, cosine out. Sine in, sine out. What happens if I put an exponential in? Exponential out. So if I did this thing, what I'd see is my output would be B e to the j omega t, like that. Now the math gets a heck of a lot simpler for it. All right, because this guy very quickly becomes, instead of this whole thing with trig identities, becomes a pretty simple algebra equation, okay, which makes it a heck of a lot easier to deal with, right? And that part we'll deal with on Monday. All right, so we got class Monday. We'll walk through that. This part here, I expect you to understand. All right, so Monday we're going to walk through that, and we'll see how we do it. It's a heck of a lot easier than this whole process. All right. The other thing that you guys learned, right, was Laplace transforms, which is another way, which is completely related to the complex numbers. All right. They're both important to understand. All right. All right. And a reminder, I've got office hours at 7:30 on Discord today.